The cab of locomotive number 447 smells like coal smoke and hot iron. Outside the windows, pine trees blur past in the late afternoon light of November 1887. Engineer Thomas Garrett has one hand on the throttle and the other resting near the brake lever. His fireman, a younger man named Cole, shovels intermittently, keeping the pressure steady but not building it. They've been descending the western slope of the Alleghenies for 11 minutes. Garrett watches the grade ahead. The rails curve gently to the left, following the natural fall of the mountain. He knows this line. He's taken freight down this stretch more than 100 times. The descent is long but predictable, 4 miles of consistent downgrade before it levels out near the timber yard at Redstone. The train behind him is not unusually heavy. 43 cars of mixed freight, lumber, machinery, bagged grain. Standard load for a Thursday run. He reaches for the brake lever and pulls it back. The familiar resistance is there, the valve hissing as compressed air flows through the line to the brake shoes on each car. He can feel the system engage through the slight tug that ripples back through the couplings. The sound changes too, just a bit, as iron presses against iron and the wheels begin their work of converting motion into heat. But the trees keep blurring past at the same rate. Garrett holds the brake lever where it is and watches the grade. He's not accelerating, that much is certain, but he's not slowing either. The needle on the steam gauge holds steady. The stack continues its rhythmic chuff. The rails hum beneath them with the same unvarying pitch. Cole glances over. He doesn't say anything, but his shovel pauses mid-swing. Garrett pulls the lever back further, adding more pressure to the line. The hiss grows louder. He can feel the system responding. There's no slack, no failure in the mechanism. The brakes are applying, but the speed does not change. The locomotive rolls on, neither faster nor slower, as though the brake lever is decorative, as though physics has quietly revised its terms. Garrett's hand stays on the lever. His eyes stay on the track, and the mountain continues to fall away beneath them, mile after unchanging mile. Garrett releases the brake lever and lets the system equalize. For a moment, he considers the possibility that the gauge is lying to him, that his sense of speed is mistaken. But the mileposts are not mistaken. They pass at intervals that confirm what he already knows. The train is holding at just under 30 miles per hour. On this grade, with no braking, it should be accelerating. With braking, it should be slowing. It is doing neither. Cole sets the shovel down and moves to the window on his side, leaning out slightly to look back along the train. The cars follow in their long, articulated line, wheels turning in smooth rotation, no visible distress. No smoke rising from the brake rigging, no skidding or chattering. Everything appears normal except for the one thing that matters. Garrett applies the brake again, this time with full pressure. The lever goes all the way back. The air line delivers maximum force to every brake shoe on every axle. In a normal descent, this would bring the train to a crawl within half a mile. He counts to 20, then 30, then releases and reapplies, testing for some mechanical lag or blockage in the system. The pressure gauge shows no fault. The response time is immediate, but the result is the same, nothing. "Check the tender brake," Garrett says, his voice level. Cole moves to the back of the cab and inspects the manual brake wheel that controls the locomotive's own rear axle. He spins it down, applying direct mechanical force independent of the air system. The wheel turns without resistance until it reaches the stop. The brake is engaged. The train does not slow. They are now 16 minutes into the descent. 2 miles behind them, 2 miles ahead. The rails curve through a stretch of exposed rock where the trees thin out, and for a moment the whole valley is visible below. Farms and a creek, and the faint grid of Redstone in the distance. The train rolls toward it at a speed that is neither safe nor entirely dangerous, suspended in a condition that has no name. Garrett's mind works through the variables: weight, gradient, friction, heat. He knows the brakes are contacting the wheels. He knows force is being applied. But somewhere in the system, something is absorbing that force without translating it into deceleration. The train is not out of control. It is simply refusing instruction. Cole returns to his position and looks at Garrett, waiting. The engineer does not take his hand off the brake lever. He holds it there, applying pressure that should matter, but does not, as the mountain continues its long, indifferent descent. At 18 minutes, Garrett makes a decision. He releases the brake entirely and lets the locomotive coast for a quarter-mile, giving the system a chance to reset. The theory is simple. If something has seized or overheated, a brief rest might allow it to recover. The train rolls freely, and for a few seconds the speed creeps upward, 31, 32 miles per hour. Then he reapplies the brake with moderate pressure. The speed stabilizes again, this time at 32, not slowing. Not accelerating, just holding. Cole watches the wheels of the tender through the gap between the cab and the coal bunker. The axles turn steadily, their rotations hypnotic and unvarying. He can see the brake shoes pressed against the wheel treads, see the contact, see the relationship that should produce friction and heat and a reduction in speed. But the wheels continue their rotation as though the contact is ornamental. The sound of the train has changed, though neither man remarks on it immediately. The usual clatter and grind of a working brake system has softened into something smoother, more continuous. The wheels no longer bite at the rails with the stuttering rhythm of intermittent friction. Instead, they hum, a low, sustained note that suggests some new equilibrium has been reached. 22 minutes into the descent, they pass the 3-mile marker. Redstone is visible now, its buildings resolving into individual shapes. The rail yard, the water tower, the depot. Garrett knows the grade levels out in another mile, and he allows himself a cautious hope that the flattening terrain will do what the brakes cannot. But he also knows that 32 miles per hour is too fast for the switching yard, too fast for the sidings where other cars sit waiting. He does not blow the whistle yet. There is no one ahead to warn, and the sound would only announce a problem he does not yet understand. Instead, he keeps his hand on the brake lever and his eyes on the track, waiting for the moment when the laws of motion remember how they are supposed to work. Cole leans out the window again, this time letting his hand trail in the air. The wind is steady and cool. When he pulls his hand back, he notices the faint smell of something sharp and metallic, like a forge at the end of a long pour. He glances at Garrett, but the engineer is already aware. The scent is coming from the wheels, from the brake shoes, from every point where metal meets metal and heat has nowhere to go. The train rolls on. The grade continues. The speed does not change. Somewhere beneath them, in the axles and wheel hubs and brake drums, a process is unfolding that neither man can see. A gradual surrender of friction, a molecular rearrangement of surfaces, a threshold being crossed without announcement. The train has entered a state of mechanical equilibrium, and it will not leave that state until something external forces it to. Under normal conditions, a descending train is a system of opposing forces. Gravity pulls the mass downward along the grade, accelerating it according to the slope. The engineer counters this with the brake system, which converts kinetic energy into heat through friction. Brake shoes press against wheel treads, iron against iron, and the molecular shear at that interface generates temperatures high enough to glow faintly in darkness. This heat radiates into the air, dissipates through the axles, and is carried away by the wind. The process is designed to be stable. The brake shoes are thick and replaceable. The wheels are massive and designed to absorb thermal load. The system can sustain this conversion for miles, maintaining a controlled descent through the simple application of sustained pressure. The engineer modulates that pressure, adding or releasing it as the grade demands, and the train slows, stops, or holds speed according to his input. But this stability depends on a critical assumption, that the friction coefficient between brake shoe and wheel remains constant. In practice, cast iron against steel produces a predictable amount of resistance. Engineers know this. They rely on it. A given pressure on the brake lever corresponds to a known deceleration rate. The math is simple. The outcome is reliable. What the system does not account for, what no engineer in 1887 has language for, is the way that friction changes with temperature. At moderate heat, iron and steel behave as expected. But as temperatures climb past certain thresholds, the surfaces begin to transform. Oxides form. Microscopic layers of material soften and deform. The contact patches become smoother, more polished, less capable of generating the resistance they were designed to provide. The brake shoes are still pressing against the wheels. The air pressure is still forcing them into contact, but the friction they produce is no longer sufficient to overcome gravity's pull on the descending train. Instead, the system reaches an equilibrium. The train descends at exactly the speed where rolling resistance, air drag, and the diminished braking force balance the gravitational component along the grade. It is not a failure in the traditional sense. Nothing has broken. Nothing has fallen off. The brakes are doing what they are designed to do. They are simply doing it in an environment where the rules have quietly changed, where heat has rewritten the equation without bothering to inform the men in the cab. The train is not accelerating. It is not slowing. It is trapped in a speed it cannot escape, held there by physics operating at the limits of what the machinery was designed to endure. Garrett does not know this yet. He knows something is wrong, but the wrongness has no visible shape. The train looks normal. It sounds almost normal. It simply will not obey. And as the grade continues and the heat continues to build, the gap between what should be happening and what is happening grows wider, until the two realities no longer overlap at all. At 26 minutes, Cole notices the color change. The wheels of the tender, visible through the gap behind the cab, have taken on a faint discoloration along their treads, a dull brownish sheen that was not there before. It is not dramatic. It does not glow or smoke, but it is visible, a stain of oxidation spreading where the brake shoes have been pressing for miles without rest. The smell has intensified. It is no longer a faint suggestion of hot metal, but a sharp, acrid presence in the air, mixing with the coal smoke and the scent of pine pitch from the forests on either side. Garrett recognizes it now. The smell of overheated brake iron, the same smell that comes from a blacksmith's grindstone after a long session of sharpening. It is the smell of friction doing work, too much work, for too long. He tests the brake lever again, not expecting a different result, but needing to confirm. The lever moves smoothly. The air pressure responds immediately. But now there is something else, a softness in the feel, a lack of the usual mechanical bite. It is as though the brake shoes are contacting the wheels through a layer of something yielding, something that absorbs force without transmitting it. The sensation is subtle, barely perceptible, but Garrett has been running trains for 14 years. He knows what the brake lever should feel like, and this is not it. Cole crouches near the floor of the cab, where a small inspection hatch allows a view of the locomotive's leading axle. He peers through and watches the wheel rotate. The brake shoe is pressed firmly against it, the contact visible and continuous. But there is no judder, no vibration, none of the small irregularities that normally accompany braking. The wheel turns as smoothly as if it were running free, its surface burnished to a near polish by the sustained heat and pressure. "It's like they're not biting," Cole says, not quite a question. Garrett nods. He has reached the same conclusion through a different route. The brakes are engaging, the force is being applied. But the coefficient of friction, the invisible number that governs how much resistance is generated, has collapsed. The surfaces are still in contact, but they are no longer gripping. They are sliding past each other in a way that generates heat without generating control. The rails ahead begin to level out, the grade softening as the train approaches the valley floor. Garrett feels a faint deceleration, not from the brakes, but from the change in slope. The speed drops to 30, then 28. The train is finally slowing, but not because of anything he has done. The equilibrium is breaking not through intervention, but through the simple fact that gravity's contribution is decreasing. By the time they reach the switching yard at Redstone, the train is moving at 18 miles per hour, still too fast, but manageable. Garrett guides it onto a siding and lets the remaining grade do the rest of the work. The train coasts to a stop against a gravel berm at the end of the spur, coming to rest with a final metallic sigh. Cole climbs down and walks along the length of the train, inspecting each wheel, each brake shoe, each axle. What he finds is uniform. Every wheel tread is discolored, every brake shoe worn smooth, every surface bearing the evidence of sustained, excessive heat. But nothing is broken. Nothing has failed in the way failures are supposed to look. The train has simply been pushed past the invisible threshold where its systems stop working as designed, and it has done so without announcing that threshold's existence until it was far too late to matter. The investigation begins 3 days later in a maintenance shed outside Harrisburg. A team of railroad engineers and mechanical inspectors gathers around the disassembled components of locomotive 447's brake system, arranging the pieces on a long workbench like a surgeon preparing for an autopsy. The brake shoes are laid out in sequence, each one labeled according to its position on the train. The wheels from the tender and the first 3 freight cars have been removed and stood upright for examination. The head investigator, a man named Calloway who spent 15 years designing brake systems for the Pennsylvania Railroad, runs his hand along the tread of one wheel. The surface is smooth, unnaturally smooth. Under normal use, a wheel tread develops a faint texture, microscopic irregularities that help maintain grip. This wheel has been polished to a near-mirror finish in the area where the brake shoe made contact. He produces a straight edge and holds it against the tread. No light passes beneath. The surface is perfectly flat, worn down through sustained contact at temperatures no one thought to measure. The brake shoes tell a complementary story. Each one has lost nearly a quarter-inch of material from its face, worn away evenly across the entire contact surface. Calloway orders one of the shoes cut in half so they can examine the cross-section. What they find is a progression. The outermost layer, which contacted the wheel, is dark and glassy, almost vitreous in appearance. Beneath that is a zone of heat-affected material, its crystalline structure altered by sustained high temperature. Deeper still, the iron looks normal, unchanged by the event. A metallurgist from the company's research division arrives on the second day with a set of testing equipment. He takes samples from the wheel treads and the brake shoes, then heats them in a small furnace while measuring their friction characteristics at various temperatures. The results are precise and damning. At temperatures below 400 degrees Fahrenheit, the iron behaves as expected. Above 600 degrees, the friction coefficient begins to drop. At 800 degrees, a temperature the wheels almost certainly reached during the descent, the coefficient has fallen by more than half. The surfaces are still in contact, still generating heat, but they are no longer capable of producing the resistance the system was designed around. Calloway calculates the thermal load. A train descending a 4% grade at 30 miles per hour for 4 miles generates approximately 1.2 million foot-pounds of energy that must be dissipated as heat. The brake shoes and wheels absorbed that energy over the course of 26 minutes, raising their temperatures far beyond the threshold, where cast iron maintains its frictional properties. Once that threshold was crossed, the system entered a feedback loop. Reduced friction meant less deceleration, which meant a longer descent, which meant more heat, which meant even less friction. The train did not accelerate because the grade was not steep enough to overcome the remaining sources of resistance: air drag, rolling friction in the bearings, and the diminished but still present braking force. It did not decelerate because the brakes, though engaged, were operating in a regime where their effectiveness had been reduced to near zero. The result was a stable speed, a mechanical equilibrium where all forces balanced perfectly, trapping the train in a condition it could neither escape nor control. One of the junior engineers asks why the crew did not notice the excessive heat earlier. Calloway points to the wheels, to the discoloration that was invisible until the damage was already done. They couldn't see it, he says. The heat was internal, in the contact patches and the hubs. By the time it was visible, it was too late to matter. The report is filed on December 3, 1887. It includes recommendations for improved brake shoe materials, for water cooling systems on long descents, for speed limits on certain grades, but it does not include an explanation that would satisfy a layman. There is no broken part to point to, no single moment of failure. There is only a train that encountered the outer limits of its own design and found itself unable to return. What happened to locomotive 447 was not a mechanical failure. It was a boundary condition. a set of circumstances where the normal operating assumptions of the brake system cease to apply. The train entered a regime of sustained high-temperature friction where the materials involved could no longer perform their intended function, and it did so gradually enough that no single moment marked the transition from control to helplessness. The core principle is brake fade, a phenomenon that occurs when friction surfaces overheat to the point where their coefficient of friction collapses. Cast iron brake shoes, when pressed against steel wheel treads, generate predictable resistance at normal temperatures. But as heat builds, the contact surfaces begin to oxidize and deform. Microscopic asperities, the tiny peaks and valleys that create grip, are worn smooth or filled with softened material. The result is a polished, low-friction interface that can no longer convert kinetic energy into heat at the rate required to slow the train. Compounding this is thermal expansion. As the wheels and axles heat up, they expand. The wheel grows slightly larger in diameter, and the axle grows slightly longer. This expansion is small, measured in thousandths of an inch, but it is enough to reduce the mechanical advantage of the brake rigging. The brake shoes, which were positioned to press against a wheel of a certain size, now contact a wheel that is fractionally larger and spinning fractionally faster. The clamping force remains the same, but the torque it produces decreases. A third factor is the long, steady grade. Unlike a steep descent where acceleration is rapid and obvious, the 4% slope of the Allegheny Western approach creates a slow, sustained pull. Gravity accelerates the train gently, and the brakes resist gently, and for a time the two forces are nearly balanced. But as the brakes heat and their effectiveness drops, the balance shifts. The train does not suddenly run away, it simply stops slowing. And because the grade is consistent, it reaches a speed where the reduced braking force, combined with air resistance and rolling friction, exactly equals the gravitational pull. At that speed, the train is in equilibrium. It is not being controlled. It is being sustained by the physics of the descent itself. This equilibrium is stable but unrecoverable. Once the brakes have overheated, there is no way to cool them mid-descent. Releasing the brakes to let them rest allows the train to accelerate, which defeats the purpose. Applying more pressure does nothing because the friction coefficient has already collapsed. Adding force to a low-friction surface does not restore grip. The train is locked into its speed, and it will remain locked there until the external conditions change. Until the grade levels out, until the train reaches flat ground, until gravity's contribution falls to zero. For Garrett and Cole, sitting in the cab of 447, there was no way to know this. They had no instruments to measure wheel temperature, no models to predict friction loss, no prior cases to reference. The brake lever felt normal. The system responded as designed. But the outcome was wrong, and they had no framework to understand why. They were operating a machine at the edge of its performance envelope, in a region where intuition and experience no longer applied. Locomotive 447 ran for another 12 years before being retired. The brake system was rebuilt with improved materials, phosphor bronze shoes instead of cast iron, ventilated wheel hubs to improve cooling. The railroad instituted new protocols for long descents, slower initial speeds, periodic brake releases to allow cooling, mandatory water stops for wet braking on the steepest grades. The lessons learned from that November afternoon became standard practice, encoded into regulations and training manuals. But the fundamental problem remained unsolved because it is not a problem that can be solved. It is a limit. Every mechanical system has a range of conditions under which it operates reliably, and beyond that range, the rules change. Friction depends on temperature. Temperature depends on energy dissipation. Energy dissipation depends on time and distance and load. These dependencies create thresholds, invisible lines that a train can cross without warning, and once crossed, the machine is no longer fully under human control. It is under the control of physics, and physics does not negotiate. The train that wouldn't slow down did not fail. It simply discovered, in real time and without permission, the edge of what was possible. And in doing so, it taught a generation of engineers that the machines they built were not as predictable as they believed. that safety margins were narrower than they assumed, and that the difference between control and helplessness could be measured in degrees of heat that no one had thought to count.